virtual address to physical address, we can see giving a request for an address. This address is virtual address. We have to locate the data in physical memory. So you must know the process of converting a virtual address to a physical address. We call address translation. This is translation. You know, we talk about some software can translate our language to your language. This software is useful when I'm in foreign countries. I don't know the language. The helpful solution. The solution is the translator software. You can see and you can use. Address translation. We can see virtual addresses can be broken into two parts. Two parts is virtual page number and offset. You can see you can think it is like a book. When I look at a book related content, I'm first finding the page and finding the row in the page. So if I give you the page and the row, you can find the content, the related content in the book. So page is like a page, offset is like row. In the book, we like the row is like offset. In Chinese, we call offset 偏移量. Okay, we can see we can calculate the size of these fields like we did with text. We can see size of is an operator. Size of can calculate the size of the object. Size of address, this is the size of address. So you can see this is virtual address have contained virtual page number and offset. Okay, this is an image of the virtual byte. You can see VPN 101 is pointing the 5 position. This is the image. Okay, address translation, we can calculate this field like we did with catch, and this is the thing from the former. Locating a physical byte, because we also divided physical memory into pages. Same process applies here. So we can see given a physical address, break the address into page number. Page number we call PPN, and the offset. Locate the page, locate the byte within the page. So offset is the row. This is some discussion. We still haven't solved our original problem. Giving a virtual address, I can find a virtual byte. Given a physical address, I can find a physical byte. But how do I go from virtual address to physical address? So this is the solution from address translation. From virtual address to physical address. So the translation is the solution. We can see each process has a table mapping. It's physical and virtual page. So PPN is the term in former class. Page table entry format, we can see this contains either PPN or indication not in main memory. We can see dirty and valid is the two format. Dirty equal page has not modified recently. Valid is valid page table entry. So we can see we like valid. Dirty is being modified recently. Access rights check on every access to see if allowed. We can see read, write, Executable is the access rights. Rights is the roles. Okay, we can see virtual page number. We can translate to physical page number. Offset can translate it to offset. So table layout contains two sections. One is VPN, one is offset. VPN, we can see the index into PT using VPN. Step 2 is track value and access rights bits. Step 3 is combine VPN and offset to translate the physical address. So the input is virtual address, the output is physical address. This is the translation step. Protection between processes with a bare system. Addresses issued with low and stores are real physical addresses. This means the program can issue any address and therefore can access any part of memory, even areas which it does own. We can see in order to create a physical address from a virtual one, we have to convert our page number, VPN, become PPN. To do this, we look up mapping for the VPN in our page table. So page table is the structure for the translation. We can only find mapping for page we own. All other mappings are invalid or blank. Therefore, we can't construct physical addresses we do not have access to. So access rights is very important. If we have access rights, we can't use the data. Yeah. So the roles, the rights is important.
Physical address is
Yeah.
very important.
Yes. So if I have keys in the classroom, we can't use the classroom. Yeah. So on the side, I have the lecture keys because the lecture teacher give us. So this is like rights, like roles. In Chinese we call 角色、权限。Private address space per user, we can see page table is in the middle. This is the page table. This is some process. This is some physical memory. So you can find some process can use page table to create the mapping from page table to physical memory. Physical memory is main memory. So the mapping is 1 to 1. You can see 1 to 1, 1 to 1. But you can find 1 to 1. This is the 1 to 1 mapping. Each program has a page table. Page table contains an entry for each program page. This is the two characteristics. Okay, we can see hierarchy page table. Hierarchical. So we can talk about how big is the page table. 64 MB RAM, 32 bit virtual address space, 1 KB page. This is the size. Okay, we can see space required by the page tables. Page tables we call PT in proportional to the address space number of users. Too large to keep in register or cache. The idea we can see keep PT page tables in the main memory. So in the main memory, the speed is fast, not in the faster or fastest, but the main memory, the speed of main memory is fast compared to physical disk and memory disk. How can we find the page table in memory? If the page table is how we learn physical addresses. This is the PT base register. We can store physical address of current page table. So you can see the image page tables in physical memory. So this is some PT in physical memory. One is access page table for address translation. Two is access correct physical address. This is the PT in main memory. Liner page table is one structure. Liner table is one structure like array. You can find the page table entry contains valid bit, dirty bit, PPN, permission bits. This is there are four kinds. We can see one OS sets the page table base register whenever active user process changes. So this is the record. Okay, liner page tables can be really large and sparsely populated. What if I only need the first page and the last page in my virtual memory space? I have to load the ancient page table. This is hierarchical page table. We can see this is level 1, this is level 2. Level 1 and level 2 is like hierarchy memory. So hierarchy structure is useful structure. When you are engineers in future, you can think about hierarchy. Yeah, hierarchy is very useful.
Yeah.
In some structure, in some computer structure, hierarchy is useful. In
the file structure, there obviously have the hierarchy.
Yes. In some companies, you know, the biggest boss is, in China we call 董事长. In English we call the boss, the big boss. What is 董事长? The biggest boss in the company. CEO, yeah. CEO is the manager, the biggest manager.
President, chairman, president.
Chairman.
Yeah.
董事会主席 chairman. The chairman is the boss of the company. CEO is the biggest manager. So in CEO we find some PM.
Yeah.
Project manager.
Yeah.
项目经理 Project manager. Ask project manager, and you can find some team leader. Yeah, team leader, and have some engineer, senior engineer, and
junior engineer.
Yeah. Some roles, some levels are in companies. In Alibaba, the level is the money.
Yeah.
If you have more high level, you have more money. Yeah. So in the company, almost engineers want to level and level. So hierarchy is very useful from the main kinds. So we use the structure in the computer organization. So please remember hierarchy. Yeah, this is level 1, this is level 2. The speed of level 1 is fast. The speed of level 2 is slow compared to 2 levels. So you can find this is index 1, index 2, and index 3. This is from Spark. Spark is one kind of OS in some company. Some company is from USA. Java is from some. Yeah. So Spark, you can see Spark is some OS operating system. Spark. Page tables in physical memory, we can use PT basic register, and we can see this is required 2 accesses of physical memory. This is 2-level page tables in physical memory. This has 2 levels, level 1 and level 2 in physical memory. Okay, we can see translation look size buffer. This is TLB. Okay, we can see translation look size buffer or look size buffer. We can see for historical reasons, cache is called translation look size buffer. And the cache is cache, and the cache is the immediate component from main memory to disk. So cache is very useful. The speed of cache, the size of cache, speed is fast, size is small. So notice what is stored in the TLB is not memory data, but the VPN becomes VPN mapping. You can see TLB vs cache. This is similar. You can see the structure is similar. Yeah, so you can see for historical reasons, cache is called TLB. So cache is TLB. TLB usually small, typically 32 to 128 entrance. TLB access time compared to cache, we can see much faster than accessing main memory. TLB usually are fully associativity. Yeah. Okay, we can see where are TLB located. Which should we check? Cache or TLB? Can cache hold requested data in corresponding page isn't in physical memory? With TLB first? Does cache receive VA or PA? This is VA, this is PA. VA is virtual address. Yeah, PA is physical address. This is miss and this is hit. Yeah, hit is correct. Miss is wrong. Yeah. Okay, this is address translation. Use TLB. We can use TLB tag to TLB in TLB. And use PPN, use page offset in physical address. We can see this is the translation. This is typical TLB entrance format. It has valid ref access rights, floating, VPN, and VPN. This is fetching data or memory read. We can see track TLB and track cache. TLB hit and TLB miss is like cache hit and cache miss. Cache hit is return data value to processor. Cache miss is fetch data value from main memory. Store it in cache, return it to processor. Page fault. What is page fault? We can see load the page of the disk into a free page of memory. Switch to some other process while we wait. Interrupt through when page loaded and the process page table is updated. When we switch back to the task, the desired data will be in memory. If memory full, replace page. LRU is one replace policy. Writing back if necessary and update both page table entries. Okay, this is context switcher. How does a single processor run many programs at once? Context switch. We can see changing of internal state of processor. What happens to the TLB? Current entrants are for a different process that all entrants to invalid on context switch. We can look VM performance and VM wrap up. Performance matrix. A matrix is some method. VM performance also use hit rates or miss rates and the miss penalty. So you can see TLB miss rate is fraction of TLB successes that result in a TLB miss. Page table miss rate is fraction of PT successes that result in a page fault. Catching performance definitions remain the same, somewhat independent, as TLB will always pass PA to catch regardless of TLB hit or miss. This is VM performance. VM virtual memory is the level of the memory hierarchy that sits below main memory. TLB comes before catch, so but affects transfer of data from disk to main memory. Previously, we assumed main memory was lower level. Now we just have to account for disk successes. Same CPI AMAT equations apply, but now treat main memory like a mid-level cache. So this is typical physical performance states. You can see this is caching, this is VM paging. This is the cache from CPU and the physical and the primary memory. Primary memory is main memory. This is the primary memory and this is secondary memory. So VM paging is in secondary memory. This is impact of paging on AMAT memory parameters. This is level 1 and level 2, DRAM and disk. This is the size and some parameters. We hope that in level 1, heat rate can reach 95%. This is high percentage, but the level 1, the heat rate of level 1 cache must reach this level because level 1 cache must reach this level. They can be reached and they can use. Level 2, you can see heat rate can reach 60% of level 1 misses. Of level 1 misses. If level 1 heat, it is not useful for level 2. If the level 1 miss, level 2 can use. So level 1 and level 2 are cooperative. DRAM has 200 clock cycles. So this is slow. This is 10 clock cycles. This is 1 clock cycle. So this is the speed. The bigger of the number, the speed, the slow. Yeah, the speed is slow. This is the disk clock. You can find this is a big cycle. Average memory access time. This is AMAT. So you can find the AMAT is average memory access time. Yeah. So you can find the AMAT. We can use calculated from several structures. We can use this is the AMAT. Yeah, AMAT is 5.5. Okay. The impact of TLB, we can see TLB rich amount of virtual address space that can be simultaneously mapped by TLB. TLB typically has 128 entries of page size. What can you do to have better performance? We can see this is multi-level TLB. This is multi-level in hierarchy level. Variable page size and the special suspended use the super page. This is not covered in this class. VM wrap up. You can see this is page-based virtual memory machine. This is the hardware page table worker. This is the data TLB. And this is the address translation. This is the hardware. This is hardware or software. This is software. So the address translation, this is the truth. You can find this is TLB miss, this is TLB hit, this is access denied, this is access committed. This is page not in memory. This is page in memory. So we can see some two choices switch. Okay. In lecture 19, we can see user program view, reality, virtual memory, and implementation. Okay. This isn't important content, so please look. Okay, we can see lecture 20. In lecture 20, we can see this topic is input and output. Input and output is the two components in the structure of ENIAC or von Neumann. In von Neumann structure, input and output is the two components in the structure. We have other three structure components. One is memory, one is calculator, and one is controller. So controller, calculator, memory, and input, output are five components in the structure of von Neumann. Okay, this is from the lecture 19. Okay, we can see this is the agenda of lecture 20. Input and output devices communicating with memory mapping. I/O is input and output. Yeah. Okay, we can see this is five components of a computer. Yeah, this is control, processor, memory, input and output. The processor, we also use calculator. Yeah. So this is control, data, memory, input and output. In China book, we call controller, calculator, memory, input, output. It is also five components. Okay, inputs have many forms. We can see keyboard and mouse, touch screen, audio input, camera, motion, fingerprint sensor. Yeah, there are many kinds of input devices. Okay, you can think keyboard and mouse is regular devices, and touch screen is like cell phone. It's like some touch screen devices, and camera audio input is like a microphone, and camera is like a cell phone and like digital camera, and some digital video. Yeah, motion is like some hat. We can draw a hat to motion and to search the motion data. Fingerprint is the fingerprint sensor. It's like in hospital we can use some in this fingerprint. Okay, we can see this is China reader. Reader is reader. In Chinese we call 雷达. Okay, this you can find we change in this. We can find the reader can touch and can detect. Output have many forms. We can see displays, audio output, printers, LED, RFID reader, This is some output. The screen, this is LED. Yes, it's also output devices. The printer is the output devices. So if we have to print some text, we must have printer, or we have to go to the printer shop and we can print some text. Okay, this is general purpose computer. We can see input as mouse, keyboard, Ethernet, Bluetooth. Ethernet is for the internet, but if we have Wi-Fi, Ethernet is not useful. So Wi-Fi is the replacement of Ethernet, but in some space, Wi-Fi isn't used. We can use Ethernet. We can use Ethernet to connect internet. Bluetooth is very useful, but Bluetooth has some shortcomings because Bluetooth had to be near to the device. When the device and the device, the distance of devices are long, are far, the Bluetooth are unuseful. So Bluetooth can link. If you have cell phone, you can link to the car, link to the computer, according to the Bluetooth. The output, we have monitor, headphones, and the Ethernet and the Bluetooth. Okay, we can see this is a cyber physical address. The input has the reader, antenna, camera, CAN. The CAN is used for bus. In some companies, some devices, some cars use CAN bus to connect to the computer. Some films display some change the car. 改装 Yeah. Some films is like Speed and 速度与激情 Some film the name of films is
Fast and Furious.
Fast and Furious.
Fast and Furious.
In the films, some conditions we can see some conditions use the computer to change the car to high level the level of car. So the CAN bus is the bus. We can't use Wi-Fi to link the car. We only use CAN bus to link the car. So CAN bus is for this use.
What's the meaning of the CAN?
Yeah. The CAN, you can search the CAN in searching engine. The CAN bus is very useful in some low level connection. We have used the cell phone and the laptop. We call in high level connection. The CAN is the low level connection. And we can say use the brake control, wheel rotation, and the CAN, and the throttle control. That is the cyber physical system. Okay. Computers without input and output, we can imagine a laptop. The laptop without a screen, without a keyboard, without Wi-Fi, without USB. The laptop is unuseful. If the laptop has not present inputs and outputs, the laptop isn't useful. So that input and output is very important for the laptop, for the computer. Yeah. Okay, what is it good for? The computer without I/O is like a car without wheels. So interesting technology, but gets you nowhere. So the input or output is important for computer. Okay, this is some I/O device examples and the speed we can see. I/O speed, this is 8 order of magnitude between keyboard and graphics. We can see this is the data rate. We can see keyboard, mouse, microphone, Bluetooth, hard disk drive, wireless network, solid state drive, and the WLAN network and the graphics display. This is some option. This is some behavior. This is some data rates. When discussing transfer rates, use SI equals 6. So this number is the biggest in the table. So we can find the keyboard and the mouse. We need low level speed, but in graphics display we need high level speed. Yeah, so the data rate is suitable for some devices. If we have a high level speed by keyboard, by mouse, it isn't used or it isn't necessary. Okay, we can see input and output devices. This is the great idea. We can see we can talk about in this section. Okay, the due discussion. Are disks I/O or memory? Or what qualities might make them one or the other? Okay, we can see this is some disks. Disks are I/O, are input and output. Disk is never accessed as memory. Pages are loaded from disk into RAM, where they become memory. The computer can run with the disk removed if everything is in RAM. We can see some process in CPU. CPU is translated process in the main memory, and from the main memory we can see the process A is from this memory. Okay, the disk has non-volatile storage and two types: magnetic drives or flash drives are two kinds of types in disks. Magnetic drives are classical drivers. We can find this is a mechanical drive and floppy disk. Information stored by magnetized fluid material on surface of rotating disk. Rotating disk is like rotate and rotate. Yeah, so the magnetic drive has some sounds. So if the laptop has magnetic drives, we can see some sounds from the drive, from the fans. So flash drive is solid state drive. Solid state drive we call SSD. SSD is like flash drive. Flash drive hasn't sounds. So if the laptop has SSD, the sound is low level. Information stored by trapping charge in the semiconductor and MOSFET-based dual-gate transistor. So semiconductor is the component in flash drive. Okay, this is a photo of hard drive internal. We can see this is a hard drive. This is magnetic drive. Yeah, we can see this is the structure. This is the head. This is spindle. This is the platter. Platter is this, and this is actual pin. So this is the arm. You can see this is the center from arm. So we can see this is we can do this operation to find. So this is the head is for right and read.
Okay.
So this is the structure of magnetic drives. So if the platters have some wrong sections, the platters have some wrong. Hard drive in action. We can see this is spindle, this is some hard drive, and this is platters, this is the center, this is the arm, and this is the logic board, and this is the connection actuator. This is how hard these drives work. Okay, this is the detail in the platters. There are some platter. In some platter, we can see this red section is sector. This green section is checker. And this is the arm. This is actuator. So several platters with information recorded magnetically on both surfaces. Bits recorded in checks, which in turn are divided into sectors. Sectors is usually by 4 kb. Okay, this is one platter. In this, we can see this is some sector, and this is sector, this is check. Okay, reading and writing from the disk, we can see actuator move the head over track. So this is some operation by seek. Seek is 5. Seek is 5. Wait for sector to rotate under head, then read and write. So you can find rotate and rotate. So the disk has rotate and rotate. Disk access time equal seek time. Add rotation time, add transfer time, add controller overhead. So we can see disk access time have several times. Seek time is time to position head to correct track, because the disk has to rotate and rotate. So in some time we must wait the correct track. Rotate time is time for disk to rotate to per sector. Transfer time is time for data to rotate under the head. So the head is the operator position. Disk device performance. We can see define performance. We can estimate some values. Rotation time is average distance of sector from head. Average rotation time equal 50% time of rotation. You know, average rotation time is the half of time of rotation time. This is average. Yeah. And 7,200 revolutions per minute is the high speed of rotation. So you can find 7,200 can become 120 revolutions per
5 seconds.
Yeah, this is the far speed. One revolution equals 120 seconds. Half rotation equal 4.17 milliseconds. Seek time is average number of tracks to move on. So this is the number of tracks and the average stick time. We can see average number of tracks moved multiple times to move across one track. Okay, faster hard disks have performance estimates are different in practice. Many disks have own disk cache and totally hidden from the rest of the computer. We can see level 1, level 2, level 3, red disk and disk. So the cache is in the middle of red and disk. Okay, this is HDD difficulties. When I used SSD, we had a light SSD because the SSD has some good things. HDD has some difficulties. You can see in the HDD, faster spinning disk with moving amplitude. What could go wrong? Had crash. Then literally the head hit into the desk surface. So you can find the head. The head has some problems, and the head has some layers. You can see some layers. You can see carbon layers, magnetic layers, and rigid metal layer, protection layer. So the structure is very complex. Fragmentation. To speed less sync and rotation time, we want data to be contiguous whenever possible. Fragmentation occurs when files are not stored contiguously on the disk. Can defrag to speed up disk. So you can see in the structure, some section are sector. This is the arm, this is the head. The head can touch some sectors, and this arm can up and down. So they can, according to some path, to touch all sectors in the platform, but the time is different. Some sectors, the access of some sectors are quick. Some sectors, the access time of some sectors are slow. It is possible. Okay, what is the average access time for a disk with the following qualities? We can see 900 tracks with 3 milliseconds for the head to cross, or 900. 10,000 RPM is the fast speed of rotation speed. If we had a quick rotation speed, disk hasn't stable because the speed is too fast. We can see disk access time, we can see sync time, and rotation time, and transfer time, and controller overhead. This is the whole section. Okay, we can see SSD. What about SSD? SSD is solid state driver. In 10 years ago, micro drive and flash memory went hand to hand. In 10 years ago, the SSD wasn't popular use in laptop. I remember the laptop in the past has the disk is popular. We can find both no volatile contains without power supply. This is important. If the SSD hasn't this characteristic, the SSD is not useful. So the main content without power is the secondary memory, the important characteristic of secondary memory. Flash benefits, we can see lower power, no crashes. So lower power is very important. The disk, what the drives, the lower power is more important. If the drives are needed more power, the drives haven't used in the laptop. So lower power is useful. No crash is important. Disk cost is important. The SSD has low and low disk cost. So in current laptop, we can use SSD. If the cost of SSD is high, the SSD can't be used in the laptop. So the cost is very, very important in Chinese market. Flash cost is the most cost divided by a bit of flash chips. Cost by bit of flash came down, become cost competitive for dense storage. So you can find came down. This is some 340 MB. This is 6 GB. This is some little drive. Flash memory or SSD technology is from main memory. You can see the structure of SSD is like main memory. It has some memory blocks, flash blocks. You can see 1, 2, 3, 4. This is some memory blocks, and NMOS transistor with an additional capacitor between gate and the source drive the drain from TRIPS electron. The performance is 1 or 0. So this is some SSD technology. Okay, flash memory has some problems. Flash has a limited number of program erase cycles. This is very important for the use of SSD, the use time of SSD. In the past, the use time of SSD is 3 years. So most customers worry about the time is short. If the SSD has short time to use, we don't pay the high price to buy the SSD. But the flash, the program erase cycle become more and more. So the use of SSD, the use time of SSD is become longer and longer. Solution is apply wear level to distribute writes evenly. Move frequently written data around. Create a map from addresses to real locations. Lie about how much space you have. We can sell 100 GB SSD. That's secret. And slowly move memory over and add section 9. So the problem, the erase cycle, the problem of erase cycle isn't the problem. So the current SSD has more and more erase cycle. Erase is like refresh. Yeah, erase and erase is refresh. This is some original iPods. This is Shuffle. This is Nano. This is classic iPod. This is Touch. In current Apple company, the iPods have several users, but the iPhones have many users. So you can find this is Toshiba Flash, we have 2 GB. This is Samsung Flash, we have 16 GB. It is Toshiba 1.8 inch HDD. This is 120, 160, 16 GB. This is the rotation disk. This is Java Nano, and this is Toshiba Flash. We can use the size of SSD. Yeah, this is some regular size in SSD. So my cell phone has 256 GB memory. Yeah. Okay. Today is enough. We can see. We can talk about it next Tuesday. And please pay attention. In some